Dear students, till now we have done Coulomb's law and superposition principle. While talking about superposition principle, we have considered point charges. There may be more than two charges around. Force on one of the charge can be found out considering different charges and finding the vector sum. Now, in place of having discrete point charges, if there is continuous charge, so we can have three different explanations or three different situations of continuous charge. Number one is line charge. Line charge means the charge is distributed over the whole line. Let's consider this as a conductor carrying charge Q having length L. The charge will get uniformly distributed throughout the length, and hence if I want to consider as the point charge, I can divide the whole conductor into small pieces and find the force experienced by charge Q due to this small charge over here can be given as per the Coulomb's law in this particular direction. It is small charge dq with length dl. Force will be small force df given by this particular direction. If these were discrete charges, we could have taken different vectors like this and added it as the vector sum. But in this case, it is the continuous charge, so the addition or summation will get converted into integration. Now, what is this charge dq? This charge dq is q by L into dl. What is this q by L? It is denoted by lambda. It is charge per unit length. This is also known as linear charge density. Hence, dq becomes lambda dl. Lambda dl. And we can consider the force due to this dq at this point by calling it as kq dq upon r1 square. Similarly, if I go to the next case when the charge is distributed over a sheet. This is a sheet, conducting sheet again, carrying charge q, will distribute over the whole sheet. So, if I consider a small piece, then it is dq, area, small area dA. What will be the charge dq? Will be given by q by A into dA. Whereas what is this q by A? It is charge per unit area. It is also known as surface charge density and is denoted by sigma. Now in this case, my point charge becomes this dq and dq becomes sigma dA. The next one is a charged body. Soon I come to this three-dimensional case. I will not call it as a conductor now, but it is some body which is totally charged from inside also, usually insulators, inside also. In such case, I can consider charge per unit volume. Now if I take a small piece out of it of dV, then this will carry small charge dq, and now I can give this dq as q by v dv, and q by v is volume charge density, or usually called as charge density, as we know mass density. Mass per unit volume is density. Similarly, now here it is charge per unit volume as charge density. Now we go ahead with the next concept of electrostatic field. Electrostatic field is simply a region around a charge. If I consider this charge, there will be a region around it where when another charge q enters, it experiences force. So now let me elaborate and explain what is this field. If I consider a charge q like this at a distance of capital Q as R, then it experiences force K capital Q small q upon R square. As you go on increasing the distance, this force goes on reducing. If you go with mathematics, it will never become zero. It will go on becoming smaller and smaller. But if you see practically, let's take example of magnet. If the magnetic poles are taken away from each other, there will be certain distance beyond which they do not experience force. So here also the same concept. Practically there will be certain distance beyond which it does not experience force. Means we have gone out of the field of this charge. This charge, when the Q charge enters inside it, it will experience force. Goes beyond it, it will not experience force. Means it will be considered as the distance infinite for it. And hence I can say the field of charge Q is within this region. Now, when I say field is of this charge, so let me call this charge as the source charge and this charge as the test charge. How we are finding out whether there is a field or not? By observing the force experienced by this charge. So, I will relate it with force now. F is equal to K capital Q small q upon R square. If I consider Q as 1, then force becomes KQ upon R square. Here what we are observing, it's only capital Q charge. There is nothing known as small q over here. So, this term will have a different name now. We call that as the field and understand it as the force experienced by unit charge. Now, when I say Q is equal to 1, I did not put a unit over here. Why? Soon I call it as 1 coulomb. We know that 1 coulomb is a very, very big charge. We have realized it in our previous lessons. That means it has to be 1 but should have a very small value. So we will reduce the unit given to this charge. For that we have millicoulomb, microcoulomb, nanocoulomb, picocoulomb, femtocoulomb. Milli is 10 to the power minus 3, micro is 10 to the power minus 6, nano is 10 to the power minus 9, pico is 10 to the power minus 12, femto is minus 15. That means as I go on gradually reducing the unit, the charge becomes smaller and smaller. Maybe I take the magnitude same as unity only. Why we have considered such unit to reduce? As I have explained just now, this is the source charge. It has its own field. This is another charge. I was calling earlier as the test charge. But this is also a big charge, means it will also have field around it. What we can see, field is a vector quantity. When the field of capital Q charge and field of small q charge start interfering with each other, two vector quantities superimposition will cause the resultant. Means it will neither be the field of this nor be the field of this. It gets modified. Soon the modification starts taking place. Means both the charges will start experiencing force. Has this charge entered the field? No, it's here, very far off. But still it has started experiencing force. So how to understand whether the field extends till here or field extends till here? That's why we start reducing the size of this charge known as the test charge. So as I go on reducing the size of this charge, the field around it will also go on reducing. So soon this will start entering it. It will start experiencing force. If I go on reducing further this charge like this, now what we can see is the field is extended up to this region. The charge is here. This distance is negligible. That means I can consider soon the charge enters this field, it will start experiencing force. Now I can call this as the test charge. So my test charge has to be a very small charge. It is testing the field of this source charge. So, to define the region around source charge, test charge should be negligibly small, but it should have the magnitude unity and positive value. Force is kq upon r square. F upon q is kq upon r square. Kq upon r square is the formula for the field of a point charge q. From here, F upon Q becomes E. If I write directly F upon Q is equal to E, this just now we have discussed, depending upon the unit on charge Q, it may not actually test the field of capital Q charge. So, this is a very important term, limit Q tending to 0. Just now, as I have explained you, as Q becomes smaller and smaller, field around it becomes smaller and smaller, and hence it can be treated as a test charge. So, for this to be a test charge, Q tends to 0, Q not equal to 0. If it is not equal to 0, it cannot experience force. It is equal to 0, it will not experience force. But if it tends to 0, means the charge exists. But soon it enters the field of capital Q charge, it will start experiencing. This is the expression for intensity of the field. As I already said earlier, field is a vector quantity because force is a vector quantity, charge is a scalar quantity. So whatever is the direction of force will be the direction of field provided my charge is positive. That is why when I said here positive, we have to ensure that it has to be positive. When it is a positive quantity, then only I can say field and force are in the same direction. If it is negative, field becomes opposite to the direction of force, and it will become further confusing. And hence, while defining field, we say it is a test charge. Test charge is negligibly small, tending to 0 and unit positive charge. As I said, field is a vector quantity, so let's denote it as a vector. Considering the Cartesian coordinate system, let me call this as the XYZ plane, XYZ region. Source charge capital Q is placed at the origin. We want to find out the field at point P, which is having position vector R. Capital Q charge will have the field at this point given the direction like this. Hence, I can say it is KQ. I will further elaborate why this direction a little later. KQ upon R square, and direction will be given by this direction only, R cap. So, vector R in the terms of the coordinates can be given as xi cap, yj cap, zk cap. If I talk about components of field, let me continue this with this first. R is equal to this. Magnitude will be square root of x square plus y square plus z square, and R unit vector can be given by this expression. Hence, the total field, if I say, can be written in this form. Now, as I said, components of field Ex, x component will be given by this, y component by this, and z component by this. Presently it is all three components over here. So x component specifically will be kqx upon this. Now let me go ahead graphically explaining you variation of field with distance. Considering point charge once again. Field is kq upon r square. So field has inverse square relation for the point charge. Field varies as the inverse square given by this graph. Now let me go ahead. As I said, I will explain why this direction in this topic. Electrostatic field lines. Electrostatic field lines are the imaginary lines on which a test charge moves if it is free to move. These lines can also be called as field lines. Let's take some examples. To start with, a positive point charge. A positive point charge is placed over here. A test charge has been brought over here. It will experience force in this direction. As I have already discussed, this positive charge, if I call it as a test charge, it is a unit charge. That means this force is actually indicating field of this charge. So even if this charge is not brought over here, this capital Q, which is source charge, is having a field in this direction. Similarly, if it is negative charge, I bring a positive charge over here, it will get attraction towards it. A force experienced by this Q charge will be in this direction. If I put the Q charge here, it experiences a force like this, because we know as per the Coulomb's law, line joining the 2 point charges. What we can see, when it is positive charge, field lines are going away from it. I will call it as radially away from the charge. If it is negative charge, field lines are entering into it. This is entering radially towards the negative charge. Hence, these lines are actually representing the field of the positive charge. Field lines of the positive charge. It is field lines of the negative charge. A little before, when we were talking about such situation, if I denote it now with the help of field lines, one is capital Q charge, another is minus capital Q charge. This has its own field. It has its own field. If these two field lines interfere over each other, obviously we understand this is a vector quantity, this is also another vector quantity. Depending upon how they are interfering with each other, there will be superposition of the two fields, and hence direction will neither remain like this nor like this. It will get modified, which is understood as they start experiencing force. So if I consider this is the region of this minus Q charge and this is the region of this plus Q charge, presently they are not interfering with each other. That means they will not experience force on each other. But soon I take them further closer, then they will start experiencing force. Now, going ahead with superposition principle and bringing two charges closer to each other. First example I have taken is two equal charges, magnitude as well as sign. Let me call this charge as 1, this charge as 2. I am considering first position as O, which is at the middle of these two charges. Then let me consider the distance as A here, distance as A here, same. The magnitude of the field due to this charge will be kq by A square, same will be for this. But if you see the direction, they are opposite to each other. As per the vector addition, they will actually subtract, will become 0. Equal and opposite fields cancel each other, and hence here the field will become 0. Let's take another point, P1. From this positive charge, number 1, field will have this direction with certain magnitude. Let me call this distance as d, this distance also d. Then magnitude wise E1 and magnitude wise E2 will be same, but the directions are different. Superposition will take place. Resultant will come out to be something like this. Similarly, another point P2 I have considered. Field due to this Q being at a farther distance will be a lesser value. From this charge 2, it is being closer, field will be larger value, and hence in the vector it has been shown with the bigger size. So what will be the direction of resultant? Resultant will be this direction. Magnitude will be En2. Here I would like to conclude, depending upon what is the position, because they have started influencing each other. Here the field is 0, here the field has certain value En1 in this direction, here the field has got another magnitude En2 this direction. Means the field is neither like this nor like this. It is getting modified in different ways. Another example if I take, one is positive, another is negative. Equal in magnitude but opposite in direction. Positive charge, field lines will be away from it. Negative charge, field will be towards it. If I consider field magnitude over here simply as kq by a square only due to this as well as this, magnitude wise they are same, but if you see now the direction, one direction here, another direction here, they both are in the same direction and hence will get added up simply 2kq by a square. But if I see this point S1, if I consider the distances to be same as L, then here field will be kq by L square with the direction. Due to this negative charge, so field direction will be towards it. Kq will be having value same as kq by L square but direction like this. So if I add these two, the resultant will come out to be some net value like this. Now considering the third point S2, again the same way, this field is smaller, this field is larger, resultant will have accordingly some other particular direction. So again we can see how the field lines are getting modified depending upon the position and signs on the two charges. So we are going ahead with modification of field lines in different cases. If two equal and opposite charges are placed close to each other, then field lines get modified like this. If two charges are equal and opposite, the field lines get modified in this manner. Third case, if the two charges are not equal, one is positive, another negative, one has magnitude 4q, another has simply the magnitude of q. Now the field lines get modified like this. What we can see, when they are same in magnitude, I can consider the symmetry at the middle. The field line symmetry in this direction is same as this direction, although the direction will be different because this is positive and this is negative. Here again, if I consider this particular at the middle as the symmetry, the field lines look the mirror image of each other. There is a symmetry, but soon one has become bigger, another has become smaller. Then the symmetry is not maintained at the middle because this is a stronger, bigger charge will create stronger field and hence field lines get pushed in this way. One is positive, another is negative. If I consider this point P, Due to positive charge, field will be in this direction. Negative charge, field will be in this direction. If the magnitude of positive charge becomes equal to the magnitude of negative charge being opposite direction, here it will be the null point, or the field will be 0. Hence, the field lines modification can be seen in this way. In the same manner, depending upon what is the charge distribution, the field lines may be parallel lines like this. It is usually with the charged sheets, or it may be like this. When we show the field lines as parallel lines like this, it indicates uniform field. That means this is also a uniform field, this is also uniform field. Here the field lines are shown closer to each other, here the field lines are shown away from each other. This indicates that the field E2 is greater than field E1. Here also we can observe, when I was talking about point charges, when we are closer to the charge, these lines are comparatively closer. When we are going away from the charge, these lines are away from each other, indicating that field is gradually going on decreasing. Field lines are closer here, farther here, indicating smaller field here, larger field here. So now let me go ahead with the properties of the electric field lines. Electric field lines are continuous curves. Whether I say this case showing as the straight lines, it is continuous. Whether I show it a system like this where it is a curvature, they are, if you see this particular region, it is continuous. Maybe the direction is going on changing, it is going like this, but the field exists throughout. It does not mean that if I show the lines like this, field do not exist here or here or here, something like that. It is continuous. But they do not form closed loops. That is why it is also considered as discontinuous. See here, if it is positive charge, it is negative charge. From here also field lines enter into this. Here the field lines enter into this. It does not form a closed loop like this. Starting from here, entering here, now starting from here, entering here. It does not happen like this. In case of the electric charges, it is a field from here to here. Again a field here to here. So in this region it is continuous, but as far as loop is considered, the continuity breaks. So they start from the positive and end in the negative. For a single charge, they appear to start or end at infinity. Now the second property is the direction of the field. When I say the field line is a curvature like this, what is the direction of field? I cannot universally say one particular direction. I have to decide by which point. This point I will indicate a tangent over here because the field is going in this direction, arrow like this. So field at this point is tangent over the curve in this direction. Next, no two field lines intersect each other. As I have already explained earlier, when they intersect means being the two vectors, they will add with each other and modify the direction. Or in another words, I can say they cannot intersect over each other. Otherwise, if I consider this point of intersection, this curvature says the field should have this direction, this curvature says field should have this direction. A single point should have single magnitude, single direction. So such situation will not occur. So the field lines cannot intersect. Next point is uniform electric field is represented by the parallel lines. Closer are the parallel lines, stronger is the field. If I talk about positive and negative charges, they attract each other. So field lines are getting contracted longitudinally. This indicates attraction between the two charges. If we talk about two similar charges, positive charges, the field lines indicate the directions like this. They are being pushed away, so they exert lateral pressure. This talks about like charges repulsion. And the last one for this particular class, the electric field lines are always perpendicular to the surface of the conductor at the electrostatic equilibrium. From here, I will continue with the next class. Thank you.